Okay, so hello everyone. I am Siddhartha Pramanik and I am a PhD student from the Department of Mathematics, IIT Kharagpur. So this is the problem solving season for week 2 of the course Computational Commutative Algebra. So in this session I will solve some problems based on the contents of week 2. So before that I will just list down the topics which have been taught in the second week. So we begin with the notion of initial term of a polynomial. So initial term, and then we have defined what do we mean by initial ideal. So initial ideal is basically a process to get a monomial ideal from an arbitrary ideal in a polynomial ring. And then we have proved the celebrated Hilbert basis theorem in a particular case. Okay, and after that so we have done the division algorithm for polynomial in several variables. So division algorithm for multivariable polynomials. And we have saw some applications of this like the uh, ideal membership problem and remainder of a polynomial after dividing by a Grobner basis. So then we have defined the algebraic varieties and some versions of Hilbert-Null-Stellenza. And meanwhile, we have also saw the structure of maximal ideals. In the polynomial ring over a field, and where K is algebraically closed. So these are the rough list of the topics which have been done in the second week. So okay, so let's start by doing some problems. Okay, so the first problem is basically I will list some properties about initial of polynomials. Okay, so first let me write down the setup. So the setup is we are always over this polynomial ring over a field with a monomial order. So if we use some specific order, then I will mention it. Okay, so the first problem. So let u, okay, let me put it as R. So R is the polynomial ring over the field K. So now let U and V belongs to R two monomials. and f and g belongs to R, two polynomials. Okay, now then, so we can take the monomial u and multiply it with f, then this is also a polynomial. Now what about the initial term of this product? So we will see that this is basically
So, yeah, I have a question. So, only you and me in the meeting or some other people?
u and
So, only you and me in this meeting or some other people is there?
uh, no, anyone with the link can join. So if you have any doubt,
Okay.
you can ask. There is no
Oh,
problem.
no, no. Actually, that I'm saying that so then we can speak in Bengali if you prefer.
No, actually, look, I have to upload it in the YouTube, so I will prefer
Oh, okay.
you
Sorry,
to.
sorry. Sorry. Okay,
Yeah,
sorry. Extremely sorry.
yeah. Okay, so it is better to. Uh, it is available for everyone.
Yeah, yeah. Okay, okay. Sorry. Extremely sorry. Okay.
Yeah. Okay. So initial term of this u f is basically if you take the initial term of f and multiply it with u. So that is the first thing. And second is, okay, before this I should mention the easier parts. Sorry, let's put it in the second. So the set of all monomials, if we take the set of all monomials of R, then there is one partial order relation like the divisibility of monomials, right? So we can say if u divides b, then we can always say that u is less equals to v. So whatever the monomial order, it does not matter. If v is divisible by u, then u has to be less equals to v. That is the first thing. And the second thing I have already mentioned. And the third is, so if we take the product of these two polynomials f and g and take initial of these things, then it is basically initial of the individual polynomials. So these things are somewhat generalization of the single variable cases. And okay, so part D, so we have taken the product, so we can take the sum also or the difference also. So let's take sum and let's ask about the initial of the sum. Then we will see that it is basically less equals to maximum of the initial of the individual polynomials. And it is an upper bound, so equality will hold if both initial terms does not cancels, actually means they have different initial terms. Okay, so these are very simple proposition. So let's see the proofs one by one. Okay, so first one is if u divides v, then we have to prove u is less equals to v. So for that, let's recall the definition of monomial order. So monomial order is a relation, so in which one has to be less equals to every monomial, and second, if a less equals to b, that will imply c times a less equals to c times b. So these are the two properties, so we will use these two. So what is given is u divides v. So that will imply v equals to some d times u, where d is also a monomial. Now, by the first property, 1 is less equals to d, because d is any monomial. Now, if we multiply u with both sides, then we will get u less equals to ud. So this is basically v. So u is less equals to v. So this is very simple. So now the second part. So we need to prove, if we multiply f with the monomial u, then its initial term is basically initial term of f multiplied with u. That means u times initial of f is the largest monomial in uf with respect to the monomial, given monomial order. So let's prove this. So let w be any term in f. So term of a polynomial means okay, in, not in f actually, it's in f. So this is a polynomial, means it is sum of monomials, right? So w be any monomial involved in the expression of f. So then w is less equals to initial term of f, because initial term is the largest term. So we can multiply with u from both sides. Then we will get u times initial f is bigger than uw. But w is any term. So this implies u times initial f is bigger than any term of uf, because every term of uf appear as u times a term of f. So this implies initial term of uf is less equals to u times initial term of f, because this term is bigger than all of the terms, so it is bigger than the largest term. But we need to prove the equality. So equality is very simple, because this term itself is a term in uf. Since u times initial of f is a term in uf, so u times initial of f is less equals to initial of uf. So you can take it as 1 and you can take it as 2. So combining these two, you will get the equality. So combining 1 and 2, we will get the equality. So this proves the second part. Okay, let's see the third one. So if we take product of two polynomials, then the initial term of the product is the product of the initial terms. So this is also actually routine check, but let's do it. So let w be a term of f and w prime be a term of g. So then we can write W is less equals to initial term of F, and W prime is less equals to initial term of G. So now here we can multiply it with W prime from both sides. So this will imply W prime is less equals to initial term of F times W prime, and here we can multiply it with initial term of F in the both side. So then we will get initial term of F times W prime is less equals to initial term of F times initial term of G. Now just combine these two inequalities. So then we will get W prime is less equals to initial term of F times initial term of G. So W is a term of F, W prime is a term of G. So their product is a term of the product of F and G, and it is less equals to initial of F times initial of G. So this implies initial of F times initial of G is bigger than any term of the polynomial F times G. So from this we can write initial term of F times G is less equals to initial term of F times initial term of G. So again we have got one side inequality, but the equality also occurs here in the same way, because this term itself is a term of the product. So since initial term of F times initial term of G occurs as a term in F times G, so initial term of F times G is equals to initial term of F times initial term of G. So this proves the third part also. Okay, so now the fourth part. So we need to prove it. We need to prove that if we take sum of the polynomials, then its initial term is less equals to maximum of the initial term of the individual polynomials. So for this we need to observe that in the polynomial a plus g, how the terms occur. So observe that every term in a plus g is either a term of f or a term of g. So initial term will be largest of all these terms, since initial of f plus g is the largest of all terms of f plus g. So clearly initial of f plus g less equals to, so it will be less equals to maximum of all terms in a plus g. So I can write it in words also. So it is maximum of all terms of a plus g. So this is basically the definition, but terms of a plus g are either terms of f or terms of g. So we can write it as, and maximum of all terms of f is initial of f, and maximum of all terms of g is initial of g. So initial of f plus g is less equals to maximum of initial of f comma initial of g. Now when the equality will hold? So if these two terms does not cancel if we add f and g, then one of these two terms will survive in the sum. So then that term has to be maximum, right? So the second part is also trivial. So if initial of f is not equals to initial of g, then either initial of f is bigger. Okay, so then without loss of generality we can assume, so we may assume that one of these two terms has to be bigger. So I am assuming that initial of f is bigger than initial of g. So if we take sum, then these two terms does not cancel out, both these terms survives, and this term is the largest term appearing in this sum, so it has to be the initial term. So clearly initial term of f plus g equals to initial term of f, and this is basically the maximum. Okay, so any questions in between?
No, sir, I understood properly.
Okay, so all the four statements are true. So we can move on to the next problem. Okay, so the second problem. So we have defined initial ideal of an ideal. So let's recall the definition first. So if we take an ideal of R, which is the polynomial ring, then from I we can get a monomial ideal, which we call the initial ideal of I. So now how to get this monomial ideal from I? So this is basically, you just collect all initial terms of all the non-zero polynomials of f and take the ideal generated by that set. So this is the ideal generated by monomials, so this has to be a monomial ideal. So this is the ideal generated by all initial terms of all non-zero polynomials of I. So there we have remarked that so okay, let me write so let I subset of R be an ideal And by Hilbert basis theorem, we know that this I is finitely generated. So give, okay, I should not write. Okay, so give an example. Give an example of an ideal I to show that the initial ideal of I may not be equal to the ideal generated by the set. So let me write it here. So it is basically the initial term of f such that f is a minimal generator. So this is a awkward way of writing, but okay, let me explain it. So I is an ideal of the polynomial ring, let's say k x1 up to xn. So by Hilbert basis theorem, I is finitely generated, let's say f1 up to fr. So the problem is saying that we need to find an example such that this if this is the generating set of I, let's say a minimal generating set, so then initial ideal of I is not equals to initial of f1 up to initial of fr. So ideal generated by these initials of the minimal generators. Okay. So that means we need to find an ideal and a generating set which is not a Grobner basis. So let R be the polynomial ring in 7 variables, and I be the ideal generated by F and G, where F is basically x1 x4 minus x2 x3, and G is x4 x7 minus x5 x6. So we need to prove that this f g, this is a f comma g, this is a generating set, but this is not a Grobner basis. So what do we mean by that? So claim is initial of I is not equals to initial of f, initial of g. Take this set and take the ideal generated by these two monomials. So one side is always true, so we need to prove that this is proper containment. So for that we need to pick an element here which does not belongs to this set, initial of f, ideal generated by initial of f and initial of g. So we need to find one element h. So let h is x7 times f minus x1 times g. So this is combination of f and g. So this certainly belongs to the ideal I. So if we write it clear specifically, then what it will be? So this is just x7 times x1 x4 minus x2 x3 minus x1 time x4 x7 minus x5 x6. So it can be easily seen that this term and this term will cancel out, and rest terms will survive. So this is basically x1 x5 x6 minus x2 x3 x7. Okay, so I forgot to tell about the monomial order. So I think it is graded lex. So let R with the graded lexicographic order. Okay, so now we have got H. So with respect to the G lex, what will be the initial term of H? So in graded lexicographic order, how do we compare two monomials? So let's say x power alpha, it will be bigger than x power beta. So how to compare two elements in G lex? So first of all, if the total degree is bigger, then x power alpha is bigger, and if total degree are same, then we just check what happens in lex. And what happens in lex means, if we take the difference vector of alpha and beta, then the leftmost non-zero entry should be positive. So here we have two terms. We need to find which one is bigger. So here total degree is 3, here total degree is also 3. So we need to check what happens in lex. So if we take the difference vector, it is 1 here starting from the first coordinate, and it is starting from the second coordinate. So definitely this one is the bigger in the G lex. So now if initial of H has to belong this ideal, then this term must be divisible by either initial of F or initial of G, but that does not happen. But so okay, we need to find initial of F also. So what is initial of F? So here also the total degree is 2, here also total degree 2, but here we are starting with the first coordinate, so difference vector 1 will be there. So this is the leading term, and initial term of G, so total orders are same, so we need to check the difference of the vectors. So this is starting from the 4th coordinate, and this is starting from the 5th coordinate. So in the 4th coordinate, we will have 1 in the difference vector. So these are the initial terms of F and G. So we can see that none of these two terms divide this initial of H, because it involves x5 and x6. And here both the terms involve x4, and x4 does not appear here. But initial term of F does not divide initial term of H, and initial term of G does not divide initial term of H. So that will imply initial term of H does not belongs to the ideal generated by initial term of F, comma initial term of G. So we have proved that this containment is strict. So we can say that F comma G is not a Grosvenor basis. Grosvenor basis for I with respect to G lex. Okay, so I hope the example is clear. Okay, so let's move on to another problem. So again, we will get back to the general setup. So let R equals to kx1 up to xn be the polynomial ring with a monomial order. And I be an ideal of R. So then the following conditions are equivalent. So first one is I is a monomial ideal. And the second one is, so for any polynomial f in R, f belongs to I if and only if every term of f is in I. So this is an equivalent condition for checking an ideal is monomial ideal or not. So I is monomial ideal if and only if. So if we take an arbitrary polynomial, then that polynomial is in I if and only if every term of f is in I. So as usual, one side is easy. So let's see which one is easy. So let's try with A implies B. So assume that I is a monomial ideal. And also let f belongs to R. So then we need to prove that if f belongs to I, then every term of f is in I, and reverse conversely, if every term of is in I, then f is in I. So one part is easy. So if every term of f is in I, then clearly f is in I because I is an ideal. So conversely, let f is in I. So we need to prove every term of f is in I. So we need to use the fact that I is a monomial ideal. So that means I is generated by monomials. So since f belongs to I, so then we can write f as summation fi ui for some I equals to 1 to n, where these fi's are in R and ui belongs to I are monomials. So these ui's are monomials and fi's are polynomials in R. Now fi's are arbitrary element of R. So since this polynomial ring is a k vector space where the monomials forms a basis, so we will use that one. So again we can write it as, so we will break this FIS as k-linear combination of monomials. So then it will look like so each Fi is k-linear combination of monomials. These Vj's are monomials and alpha aj are scalars. Alpha aj belongs to k and Vj are monomials of R or in R. So we have assumed that these ui's are elements of I. So since ui belongs to I, so Vj times ui also is in I because I is an ideal. In fact, alpha ij Vj is in I, and these are the individual terms of the polynomial f. So every term of f appears like this term. So that will imply every term of f is in I. So first we have break down f as combination of sum of monomials. Then we have break these polynomials as combination of k-linear combination of monomials to see how the terms of f looks like. So A implies B is already proved. So now B implies A. So we need to prove that if this condition holds, then I is a monomial ideal. So assume the condition in B and we want to show I is a monomial ideal. So for that we need to prove that I is generated by a set of monomials. So let X be the set of all monomials which are in I. So all monomials in the ideal I. So claim that this ideal I is generated by the set X. So again one side is clear, so we need to prove the uh, reverse containment. So let F be an arbitrary element of I. So we need to prove that this F belongs to ideal generated by X. Now by the condition that F is in I, that will imply every term of F is in I. But term means monomials, right? Now we can write F as summation C alpha U alpha, because monomials forms a basis. So C alphas are in K and U alpha are monomials. So this C alpha U alpha are the terms of F. So since C alpha U alpha, or just U alpha, sorry, we just need the monomials. U alpha is in X, so that will imply summation C alpha U alpha belongs to ideal generated by X, and this element is basically F. So this implies I subset of ideal generated by X. So I is generated by a set of all monomials in I. So I is a monomial ideal. Okay, so let's do the next problem. So in Dixon lemma, we have seen that every non-empty collection of monomials has a finite set, the minimal set of monomials in that set has to be finite. So using that, we can say something about the generators of a monomial ideal. So let I be a monomial ideal in R. Then prove that I has a unique minimal monomial generating set. So I is a monomial ideal, so it has a monomial generating set. But using Dixon lemma, we can say that it has a unique minimal monomial generating set. So this unique minimal, this part is important. So using this thing, we can say some more things. So I will list down those things after this, but let's prove this now. So since I is a monomial ideal, so it has a monomial generating set. Okay, so let's say it is G. So then G is a non-empty set of monomials. So by Dixon lemma, the minimal elements in G is a finite set. So then this minimal set can be used to generate I. But if we take different G, we can get different minimal set. So we will prove that whatever G you take, you will get only one minimal generating set. And both sets are finite. So we can assume two monomial generating set, minimal monomial generating set. So let G1 equals to U1 up to UR and G2 equals to V1 up to Vs be two minimal monomial generating sets. Generating sets for I. So we need to prove two things here for uniqueness. First one is this R has to be equals to S and this Ui is equals to Vj, means these elements are same up to some permutation of the indexes. So to prove this, since U1 belongs to I and this is generated by G2, so this will imply that some Vj will divide U1. So for some J, because U1 is a monomial and U1 belongs to this ideal generated by this set. So this will imply U1 equals to some D1 times Vj, where D1 is a monomial. So again, we can play the same game with Vj. So Vj is an element of I, which is generated by G1 also. So that will imply some Ui will divide Vj. And that will imply Vj equals to some D2 times Ui, where D2 is a monomial. Now let's put this D2 times Ui here. So then U1 equals to D1 D2 times Ui. But what we have assumed is these sets are minimal generating sets. So none of this uy is divisible by the other uj's. So from this we can say I has to be equals to 1 and d1 times d2 is 1 because g1 is minimum. So if I is equals to 1 and d1 d2 is 1, so then we can say vj is equals to u1. So that will imply vj is equals to u1. So if you continue this process, so continuing this, we will get this r is equals to s and vj will be u of some sigma I, where sigma is a permutation of the set 1 to r. So this proves the uniqueness of the minimal monomial generating set. So every monomial ideal has a unique minimal monomial generating set. So this is a consequence of the Dixon's lemma, which we have used in the beginning to get the finiteness of the monomial generating set. Now using this I will list down some other properties, but I will not prove this because they are just routine checks. So let I and j be two monomial ideals in R. Then first of all we can take different operations to get new ideals. So if we take the sum, then this will also be a monomial ideal. Not only sum, we can take the product. So these two are basic operations, and one more operation is the intersection. So these are monomial ideals. And even we can find the unique minimal monomial generating set for these ideals in terms of the unique minimal monomial generating set of I and j. So that you can try to prove. The other operations are, you can take radical of I, and also you can take a colon of two ideals. So these are also monomial ideals. So I will not prove this. These are not difficult, but one may refer to standard text. But it's worth to know these things. Okay, so far, do you have any questions or any doubts?
No, sir, it's okay.
Okay. Okay, so let's do some problem from the practice problems. So let I be an ideal of R, where R is the polynomial ring kx1 up to xn with a given monomial order. Then prove that uh, 1 belongs to I, that means I is the whole ring, if and only if 1 belongs to G for any Grosvenor basis G of I. So I think this fact has been used in the lectures, but let's prove this now. So one side is clear. So if 1 belongs to G for any Grosvenor basis G of I, then clearly 1 belongs to I, and I has to be the whole ring. So we have to prove the other way. So conversely let let 1 belongs to I, and also let G be any Grosvenor basis of I. So we need to prove that 1 belongs to G. So 1 belongs to I, that will imply, so observe that 1 itself is a monomial, or or more generally what I mean is 1 is itself equals to its initial term, and it should be belongs to the initial ideal of I. So that means 1 that means U divides 1 initial of U. So initial term of U divides 1 for some U in the set G, because G is a Grosvenor basis. So some element U from the Grosvenor basis, initial of that U will divide 1. So that will imply initial of U has to be less equals to 1. But 1 is the smallest of all monomials. So that will imply that we have proved in the beginning. So this implies initial of U has to be 1. And initial of a monomial is 1, that definitely imply U has to be 1, and it is in the Grosvenor basis G. So was 1 is in I, that will imply 1 belongs to any Grosvenor basis G. So this is a very easy fact, but sometimes it is very useful. Okay, so let's do one more problem from the practice problems. So it is about the finding the initial terms of some polynomials. with respect to the graded reverse lexicographic order. So find the initial terms of the following polynomials with respect to graded reverse lexicographic order. So the polynomials are f1 equals to x square y plus xy square plus y square. f2 is equals to xy minus z. f3 is equals to y square minus xz. And the ring is here polynomial ring in 3 variables x, y and z. So one can do this easily in Macaulay too, but now let's do it by hand. So first recall how the ordering is defined, means how the graded reverse lexicographic order is defined. So if you take x power alpha and if you take x power beta to monomials, then when we will say this one is bigger in graded reverse lexicographic order. So if the total degree is bigger, so if the total degree of x power alpha is bigger than total degree of x power beta, then we say x power alpha is bigger. Or if the total degree is equal, then what we do is we just check the difference vector alpha n minus. So this is the difference vector and we look at the rightmost non-zero entry. So the rightmost non-zero entry should be negative. So in this vector, the rightmost non-zero entry is negative. So if one of these two conditions hold, then we say x power alpha is bigger than x power beta. So here we need to check by these things. So first we need to check the total degree. So let's try for the f1. So total degree of y square is 2 and total degree of these two terms are 3. So definitely the initial term must be either this one or this one. So what happens for f1? So this total degree are same. So we need to check the difference vector. So for this, the difference vector is 2, 1, 0. And for the second one, the difference vector is 1, 2 and 0. And the difference is basically 1 minus 1 0. So the rightmost non-zero entry is minus 1, which is negative. So x square y should be the bigger term with respect to graded reverse lexicographic order. Now for the second one. So second one is simple because total degree of xy is 2 and total degree of z is 1. So it is basically x times y. And what happens for the third one? So here total degree are 2 for the both terms. So we need to check the difference vector. So it is 0, 2 0 minus 1 0 1, which is basically minus 1 2 minus 1. So the rightmost non-zero entry is minus 1, which is negative. So y square is the bigger term with respect to g reflex. So you may try to check these things in Macaulay too, which will be a good practice. Okay, now let's do some problems which will help to do the assignment problems. So it is a true false type question. So the ideal I generated by x comma y minus 5 comma z plus 2 in the ring kxyz contains the ideal x times z plus 2 comma y minus 5 comma x square plus y square. So this ideal I contains this ideal. So let's put a name for this J. So I contains J or not. So try to think this for a few seconds. So we need to check that J is subset of I or not. That means these three polynomials are in I or not. So how to check? So that is the direct way of doing these things. But there is one more convenient way of doing this. Okay, so do you have any guess for this question?
So here x square plus y square, I think may not be in that ideal. Like that, we can do something.
So how?
I mean, I
Okay,
mean, if J subset of I, then it is enough to show that all monomial generator inside the I. So we can do like that.
all, but these are not monomial ideals.
Yeah, these are not. Sorry, so these are not monomial, but we can check like that whether it is very clear that x into z plus 2 in the inside I, y minus 5 inside I. So it
Yes,
is enough to check x square plus y square is inside I or not.
yes, yes. So how you will check that x square plus y square is in I or not?
So if x square plus y square inside I, then we can express it as a x times some f xyz polynomial plus y minus 5
Yes.
into some g xyz. So like that we can check. Uh, yeah.
Yeah, but yeah, the process is okay, but I think that will be laborious. So what is the convenient way of doing this is, so note that this I is a maximal ideal in kxyz. So note that I is a maximal ideal in R. I hope that is clear.
Yes.
And what is variety of I? So maximal ideal corresponds to points by Hilbert-Nullstellensor. And variety of I is basically the set of all points in K3 in which all these three polynomials will vanish. So if x has to vanish, then the x coordinate should be 0. And y minus 5 has to vanish, then y equals to 5 and z equals to minus 2. So the point corresponding point is 0, 5, minus 2. So this is a singleton set. Because I is maximal ideal, this has to be a singleton set. Or we may assume K is C. So one may ask that for Hilbert-Nullstellensor sometimes we need algebraically closed fields. So variety of I is this singleton set. So if J is subset of I, then if we take the variety, then V of I has to be subset of V of J, because V used to reverse the containments. So that will imply 0, 5, minus 2, this point must belongs to variety of J. Sorry, must be in variety of J. So that means all elements of J has to be vanished at this point. Now check about this x square plus y square. But x square plus y square does not vanishes at zero, 5, minus 2, because it will be 0 square plus 5 square, which is 25. So this implies J cannot be subset of I. So is it okay, or do you have any doubt?
No, sir, it is very clear.
Okay. So I feel this is a more convenient way of doing this, because the fact is this ideal is maximal and variety of this is a singleton set. So if variety is more than one point, then there might be some difficulty, but in this case it is very simple. Okay, let's do one more basic problem which is very easy also. So find the maximal ideals of the ring, let's say qx modulo x power 4 minus 1, ideal generated by x power 4 minus 1. So this is a ring. We need to find all maximal ideals of this ring. So how to do this thing? So this is basically quotient ring of qx, where we are taking modulo by x power 4 minus 1. So there is a relation between the maximal ideal of a ring and its maximal ideal of the quotient of this ring. And what is that? So this is called the correspondence theorem. So by the correspondence theorem, so if we take maximal ideals of qx mod x power 4 minus 1, the set of all maximal ideals of this ring, then this ring is in 1-1 correspondence with maximal ideals of just qx and those maximal ideals which contains x power 4 minus 1. So here is 1-1 correspondence. So we need to find this set. I mean the maximal ideals of qx which contains x power 4 minus 1. Now how the maximal ideals of qx looks like.
So it is basically generated by irreducible elements. I mean, it is a PID, so it is generated by irreducible elements.
Yes, so qx is a PID. So
And
every
also, yeah, so if it is maximal ideal, then it will be prime. So, and x to the
yes,
power 4 minus 1 inside. So we can use the primeness of this one, and we can say like that x minus 1
yes, yes,
by x to the.
yes. So you are thinking in correct way. So just let me write down in a proper manner so it will be clear. So since qx is a PID, so every non-zero prime ideal is maximum. Prime ideal in qx is maximal. So this is one fact. And principal ideal, PID means principal ideal domain, so it is generated by a single element. So if M containing x power 4 minus 1 is a maximal ideal, then M has to be generated by some polynomial Px, where Px belongs to Qx is an irreducible polynomial. And it's a PID, so it's a UFD. So irreducible and prime elements coincide. So Px is a irreducible, or we can say it's prime element in Qx. So x power 4 minus 1 belongs to ideal generated by Px. That will imply Px must divide x power 4 minus 1. So that means Px has to be a irreducible factor of x power 4 minus 1. So what are the irreducible factors of x power 4 minus 1? So x power 4 minus 1, we can write it as x square plus 1 times x square minus 1. Again we can break the second term like x square plus 1 times x minus 1 times x plus 1. And you can check that this is the irreducible factorization of x power 4 minus 1. So Px has basically three possibilities: x square plus 1 or x minus 1 or x plus 1. And since these three polynomials are irreducible, they corresponds to maximal ideal. So there will be only three maximal ideals. Hence there will be three maximal ideals which contains x power 4 minus 1, means there will be three maximal ideals in the quotient ring. So in a similar manner one can find the prime ideals, but in this case all these prime ideals are maximal, but in other rings also one can follow the same approach to find the prime ideals. And once you find the prime ideals, you can use that to compute other things like the nil radical and the set of all zero divisors, all those things, because the nil radical is the intersection of all prime ideals. Okay, so so far any doubts or any
No, sir, it's
questions?
okay.
So you can ask questions if you have any problem in the lectures also. So
Oh, okay.
so so far what we have done. So we have done initial term, initial ideal, Hilbert basis theorem we have talked in the previous week, I think. Division algorithm I have not talked much, but it's okay. Varieties I have used. Null-Stellenza also I have used. And structure of maximal ideals also we have seen. So I think I have covered all the parts. So maybe if there is no doubt, then I think I will stop today. Or if you have any doubt, you can ask me.
No, sir, I think it is okay today. No doubt.
Okay. So I think there are very few people have taken this course. That's why only
Oh,
one student is there in this live session.
yeah, so I am here only. That's why I asked.
Yeah, I don't know why, but yeah, it's okay. I have no problem because although I have to upload in the YouTube, so might be people can see
Okay,
it from there.
so can I, how to, can I join you personally? I mean, can I get your number or something? Uh,
Number means what number? Phone number you are
I
asking?
mean, what phone number or WhatsApp number, something.
Yeah, maybe. Okay. Okay. So let me stop the session now. Then maybe we can
Yeah,
talk.
yeah.